Hey everyone, and welcome. Today, we're going to crack the code on something that's at the absolute heart of industrial automation. We're talking about how the brains of a machine, these controllers, actually see and interact with the world around them. I mean, really think about it. When you see a giant robotic arm moving with perfect precision, or a conveyor system sorting hundreds of packages a minute, how does it all actually work? It can seem like magic, right? Well, today, we're pulling back the curtain to show you the simple and honestly elegant logic behind it all.
You see, the big secret is that these powerful controllers, we call them PLCs, or Programmable Logic Controllers, they don't understand words like start, or stop, or hot, or cold. Nope, they speak a much simpler language. For them to control anything in our world, they first have to translate it into their native tongue, the language of binary.
And that's literally it. Every single physical thing, from you pushing a button to a sensor seeing a product on a line, gets boiled down to one of these two states. Is there voltage present? Yep, that's on. Is there no voltage? Well, that's off. This incredibly simple two-state system is the rock-solid foundation for everything else that happens.
Okay, so you might be thinking, if everything is just on or off, how in the world do we handle more complex stuff, like, say, temperature readings or precise motor speeds? Well, we do it by grouping these simple signals together into larger, more meaningful structures. So let's dive in and look at the actual building blocks.
So, the most fundamental, the absolute smallest piece of information is the bit. That's the single on or off state we were just talking about. We use a 1 for on and a 0 for off. And the light switch analogy? It's perfect. A switch can only be up or down, on or off. This is the atom of the PLC world.
Now, one light switch by itself can't tell you a whole lot. But what if you lined up 8 light switches in a row? Whoa! Suddenly you can create all these different patterns of on and off, and you can represent a whole lot more information. This group of 8 bits is called a byte, and it's the very next step up in our data food chain.
And this is a great way to see that relationship. By combining just 8 of these individual on-off signals, a PLC can now represent numbers from 0 all the way up to 255. That is a huge leap in capability from just a single bit. It's enough to do things like define the specific speed of a small fan, or even represent a character like the letter A.
But for even more precision, for more power, PLCs often group 2 of those bytes together. And that creates what we call a word, which, as you can see, is made up of 16 bits. This is an incredibly common data size you're going to see everywhere. With 16 bits, it can hold much larger numbers. We're talking over 65,000 different values. This lets it store really precise information, like the target speed for a conveyor belt down to the RPM, or the exact temperature needed in an industrial oven.
So, just to lock this in, the crucial thing to remember is this hierarchy. We start with one lonely bit. We group 8 of them together to make a byte. And we group 16 of them, or 2 bytes, to make a word. This is exactly how a PLC builds up a detailed picture of the real world from a bunch of simple on-off signals.
Okay, so now we get what the data looks like. But how does the PLC know where to find it, right? How does it tell the difference between the start button and the stop button if they're both just bits? It does this using a really clever system called addressing.
And honestly, that's the absolute best way to think about it. Just like your house has a unique street address so the mail carrier can find you, every single sensor, every switch, every motor, and every light connected to the PLC has its own unique address. That way the PLC's processor knows exactly where to look to check its status or where to send a command. No confusion.
So an address isn't just some random number. It's got a very specific structure. It tells the PLC 3 critical things. First, what type of thing is it? Is it an input or an output? That's the identifier. Second, which group of 8, which byte, is it in? And third, which specific bit, from 0 to 7, inside that byte are we actually talking about?
And this is where it all comes together. Check this out. Look at that first example, I.0.1. That address is telling the PLC, hey, go look at the inputs, then find byte number 0 and tell me the status of bit number 1. See? It's a super precise, unmistakable instruction. And the exact same logic applies to outputs, which we often see with a Q or even internal memory bits.
Now, here's a really crucial real-world detail you have to know. While this concept of addressing is pretty much universal, the exact letters and numbers that are used, well, they can change. The best way to think of it is like different dialects of the same language.
So while using I for input and Q for output is super common, it is not a universal rule. As the source material for this explainer points out, you might run into some manufacturers that use a completely different letter, maybe an H for certain types of memory. The structure, identifier, byte, bit, is usually going to be the same, but those specific letters, the dialect, can definitely vary.
And this right here is the key takeaway for anyone working in this field. You can't just memorize one system and expect it to work everywhere. The real skill is understanding the fundamental structure of an address, because then, when you run into a new brand of PLC, you can quickly figure out its specific dialect.
All right, so let's do a quick recap. We've seen how PLCs take our messy analog world and translate it into simple on-off signals called bits. We've learned how they group those bits into bytes and words to understand more complex information. And we've seen how every single device gets its own unique address, like a house on a street, so the PLC knows exactly where to find it, even if the street names or the naming conventions change from one brand to another.
So we figured out how the PLC translates the world into data it can understand and how it keeps all that data perfectly organized. But that's really just the first step. The real power, the magic, comes from what the PLC does with this information. How does it use input I0.1 to decide exactly when to turn on output Q2.5? Well, that is the magic of PLC logic, and it's a topic for another day. Thanks for joining me.